Okay, yeah. So great that all of you are here for my presentation. So before I start, I would absolutely thank Bernd for bringing up the idea to have the workshop here. I mean, that was an excellent idea, and for Thomas bringing up the location, right? And I went out in the morning and had some impressive pictures of the mountains with the sun rising there. So it's really beautiful here. So, since all of, I have to switch on this. Yeah. Since all of us start with a little historic view back, I want to do the same thing. So I had troubles to come up with a good title for this slide. So I used it, journey from HPC to embedded, but it's actually not true. Before I started doing computer science, I really liked to solder things together. That was the time when the first little microprocessors came up and the 74 ICs and so on. So that was a big motivation for me to go into that direction. And then when I was in Munich from 1991 onwards, I think, or two, something like that. We worked on distributed shared memory. So that was a time where the message passing machines came up, the distributed memory. We all learned that it's difficult to program these guys, right? And so we had the history of HPF, High Performance Fortran, and Hans Zimmer and our group developed this superb system. And so that was already trying to get around the programming problem to parallelize sequential applications for these machines. But we also learned that this is difficult for these sparse or irregular codes, right? So for the regular ones, it worked quite nicely, but for the others, it was really tough. And so another approach was the distributed shared memory, right? So that you actually emulate a shared memory or shared virtual memory based on the virtual memory support in the operating system. And so we had a good collaboration with Intel at that time here in Munich, because they actually also had a group in Munich that was developing software for the Paragon machine that was in Jülich at that time. And so we came up with a programming model which was basically sort of OpenMP directives for shared memory programming and annotations for affinity, something like that. And part of that was the Opal, which was a performance analysis tool. So we tried to actually show people related to the source code and the data structures where they have local and remote accesses, right? So not to go very deep in the low-level generated code, but to alleviate the information to the programming level of the application. And that was then the time where the idea of Apart was born, when Bernd joined and so on. And so I was very much inspired by the work of Bart and Paradigm. So that was really very important, because you had this hierarchy, you had the dynamic instrumentation, insert, whatever you want to know dynamically. So I found this very stimulating. And the Opal was a classical way that you instrument the source code and you then afterwards, post-mortem, you analyze the data. So that's what most tools have done in the past and are currently doing as well. And when I came to Munich, I met these people from the chair there, right? And Thomas, you were probably there, and you had developed in this SFB, right? These online tools. So that was your big thing. And I spoke to Roland, and he convinced me that we have to go to online, right? So, and that was the birth of the periscope system. And I could find this diagram that highlights a little bit what the components were. It was really an online tool because we had this agent network. We could distribute a number of agents over the machine. And while the application was running, the agents searched for the performance problems. So we did not go for the binary instrumentation, but we stick with the source level instrumentation. But we had ways to configure it so that we only collect the information that we currently, for our hypotheses, actually we need to verify whether they are true or false, right? And so let's see. Yeah, it was Paradigm was really an important idea there, and the IPSC tools. I don't remember the name actually. So you had a special name for this. TOPSIS, right? TOPSIS, yeah, right. And so then, we came up and implemented this periscope tuning framework, and that was, then there was this collaboration with Jülich and the other guys developing SCORE-P. That was not always a very smooth collaboration, because we were the only ones that wanted to have this online interface there, right? But it worked well for quite a number of years, as Bernd said. Yeah, we got a lot of funding, and it was very helpful for me. So, and at some point we extended this for tunings, for automatic tuning. So we developed tuning plugins, and Eduardo was part of that effort. And so we could actually not only analyze the bottlenecks, but actually tune the application on the fly, assuming that it has a repetitive behavior, what is very common to these applications, and you can actually use what you learned in one repetition to do the next thing, right? Good, so that was Periscope. In the HPC field, we then had one of these big research centers that came from embedded people, collaboration with Karlsruhe and Erlangen, called Invasive. They used the term invasive programming, and they had these starships going to the processors and invading processors in the machine. And so we joined it with the idea that we could use this invasive programming also for MPI, for a classical HPC. Yeah? And classical HPC is still, you have a very static distribution of the resources. And so the idea was to actually make this more dynamic, so that applications during the execution can grow and shrink, so they can use more or less resources. We first did it for OpenMP, and then finally for MPI, and we developed IMPI. That was done by Isaias. Compress was a main person, but I think you also contributed, and there's Joffin was sort of active in that area. So there were still the people that worked on that are around, and this idea of IMPI is now continued in the Euro HPC project for Martin. And Isaias is part of that as well, and put on a more solid basis for the standard MPI, right, based on the session concept. So I moved on to look a little bit into the cloud, and I had a very good student working on predictive autoscaling for the cloud. Yeah, so the cloud's a big advantage is elasticity, right? That's the most interesting point from my point of view. So you can actually scale applications according to the needs of the users, right? So, and you try to do this predictively, because starting new virtual machines take quite a bit of time. So if you know ahead what will happen with the number of requests and so on, so you can actually scale the application automatically, right? So another activity together with Huawei in Munich is AI Ops. So the operations of these clouds require to supervise or monitor a big infrastructure, lots of applications and so on. So you try to apply AI to that, right? And so the student who is currently, who finished but still has to do the PhD exam, developed concepts for root cause analysis based on logs, and also for failure prediction in optical networks, and I think related to this in the cloud. Right, and then Anshul Jindal from my group actually continued in the direction of function as a service. And so that means these are offerings in cloud where you actually don't have to care about servers anymore. You just write functions which are triggered by events, and they are actually executed in the infrastructure that is provided by the cloud providers. And so that was extended so that you can actually go over heterogeneous systems, different cloud providers, cloud, edge, function as a service platforms, and so on. And so as a retrospective, we are currently, I have also one student looking in elastic workflows in automotive. So that is the idea that, not only you can make MPI applications dynamic, but also workflows. So in BMW, they run the workflows in a very inefficient way on their local cluster. And so we want to use the cloud for that, and that actually you have resources allocated to the workflow, but if the workflow can use more or less, it can, for example, lend resources to others so you don't have to pay for it and so on. So that is the basic idea behind that. Good. Then we have Fatless, and the person behind Fatless, federated learning, is Mohak. Besides a lot of other things, he talks about something else today. Finally now I'm much interested in the cloud edge continuum for IoT. And I will talk a little bit more about that, right? So what is it basically? So you have these IoT devices which are on the device layer, and these can be quite complex. Yeah? So these are typically, you have really battery-powered sensors, actuators there, and so you have to be very careful about managing your energy. So it's a totally, energy is much more important, I would say, than in HPC systems, and it's a very different level of management. And so you really have to understand the resources that you use for your application. So you have, for example, normal cores. You have multi-core nowadays, even in these microcontrollers, using a few microamperes in sleep mode or a few milliamperes in active mode. You have networks, Wi-Fi, whatever. You have ultra-low power cores there, and you might even have accelerators in these nodes, right? You see some images. That is the one we are currently most interested in. It's an ESP32 S3, which has a vector unit. And then there are also FPGA-based boards, or Google Dev Board, for example, which has a TPU where you can actually accelerate your artificial intelligence, whatever inferencing that you want to do, right? So on top of that, you have the edge layer. So in the edge, you have this, basically the gateways for the network, and to the gateways, you also have edge servers, right? And so these edge servers typically are connected to the power grid, but we could definitely imagine also that these edge servers harvest energy. So in looking at the importance of energy harvesting and green energy, it would be interesting to also look at this layer with respect to best use of the harvested energy here. These are typically individual machines, individual servers with own disks, or can be even clusters with different size of servers. And that is what we have currently for experimenting. So these are basically fanless servers. So that is what people want to have. You put it on the edge, you want to have a very resilient system there, right? And fans seem to be one problem, right? And so we have quite a number of different machines which have a GPU, some don't, have different processors in there and so on. So that is what you can expect to see on that layer.
Michael.
Yes.
When you say energy.
Yes.
Do they normally have air cooling?
No, they should not.
So exactly. So because it's no additional cooling. It is the normal way to cool the device.
Yeah, even no air, because they're passive cooling.
Yeah, passive cooling.
Yes.
Thank you.
And so then there is this privacy layer and privacy barrier that is important for the use case we look at. So I will explain at the end. And then we have obviously the cloud on top of that. And the cloud actually has these big data centers there. They are connected to, obviously the power grid. They might use green energy or brown energy. And you can obviously also optimize for using green energy. There's quite a bit of work, and also MOAG did some work in that direction already. Good. So the background for what we are currently trying to do is the FDN, the Function Delivery Network. And Thomas, you know about that, right? Because of the thesis. So basically, we developed a system where you can actually connect a number of different cloud platforms for function as a service. So you schedule functions on this platform and that they are executed. These invocations are executed there, right? And so we have, for example, here an Amazon AWS cluster. We have Google, I think that's Google, CloudFormation, Google. We have a private cloud cluster in the LRZ Compute Cloud. And we also have an edge cluster with some Raspberry Pis and so on. So that is a bit older stuff there. And all of them are basically running this function as a service platform, right? And invocations actually come to the top of this, to the control management cluster here, and then there is a courier load balancer which actually distributes these to the clusters. And the idea is that you load balance it with respect, for example, the data access or the service level objectives that you have to do it at a certain deadline with respect to the capacity or energy. And Anshul developed quite a number of scheduling approaches for that. And we also, for the performance analysis, we have the FDN monitor here. So this basically interfaces whatever monitoring system is on this platform. And so we collect this information in an InfluxDB and use Grafana for visualization. So nowadays you have quite a number of very powerful tools available to build similar things like we have in the HPC world. So this is, yeah.
Do you leverage containers for your instrumentation at all? Do you somehow?
Yes, it's all container-based, yeah.
Do you somehow use the fact that do you somehow use the container as some kind of mechanism for instrumentation, or, like getting whole systems?
Well, the software for the monitoring is basically deployed in containers, right? So it's Prometheus, for example. And then you exploit that the management is Kubernetes, and you get measurements from there. You can get measurements from your own software, and so on. Yeah. But basically, the installation, everything is container-based nowadays. All right. Good. So you see, you can look at the dashboard of the infrastructure. You can see the CPU usage and so on. So all what you would expect, you can do. We also have a dashboard where you can actually follow the functions, right? So you have certain functions are deployed to the system and executed. So you can know how they behave on the different machines, what the response time is, whether you have failures and so on. Good. So this is there. And we want to, the criticism I have is that all the function invocations basically enter on the top. Right? So you have to go to a central location, and from there you distribute it according to optimizing for SLO, for example. So, and this definitely has to be extended that function invocations can actually enter also from below. And so we are now going to extend this for IoT, and the idea is that we basically have on all the layers, across all these layers, we basically use these functions and the concept of function as a service to execute computation. We have events that trigger functions, and we have a data store. And we want to have a key value store which is distributed over the layers, and where you then can optimize the location of replicas, for example, according to the needs of the scheduling of your function invocations. So the whole goal is to do optimizations, right? And there are 3 dimensions where you can actually optimize here. So you can, for example, optimize within a layer. So let's say you have your microcontroller, the sensor there, right? So you can now shift invocations between the different cores, for example, to reduce energy consumption, even on this very low level. You can obviously do the same on the edge level, right? And you can do that on the cloud level as well, right? So you can basically optimize within the layer, no? So you could shift to a data center that provides more green energy at the moment, something like that. Huh? The other thing is you can actually optimize by shifting across the layers. So think about your little microcontroller that has to do object detection on images from a camera. So that takes quite a bit of energy, right? So you could actually offload these invocations that do the inferencing, and you can offload it to the edge, right? Or even to the cloud. Obviously, you have to know what the deadline is, right? And what data are required. But by doing that, you could reduce the energy consumption of your low-level device, which might be very important because you want it to survive, no? And not die because of shortage of energy. Right, and we can even optimize in time. So we can shift these invocations in time. Good example on the low level is that you actually you want to offload the computation to the edge, but you actually don't want to start the wireless connection all the time because it takes 100 milliamperes instead of 20 milliamperes without that. So you actually want to batch these things, put it together, send it at the time you actually activate the wireless connection, right? So you could also think inside of your sensor. If you have an accelerator, you can wake up the accelerator, and then you process 10 pictures, and then it goes to sleep again. So we can shift in all three layers, right? And that's what we want to do. So this is implementation of the serverless IoT framework on the sensor, on the device level. So basically, you can see here that we have triggers. These triggers generate events. They go to an event queue. We have a scheduler which would know about the functions and the subscription of the events, and would then actually decide which function invocations to run where and when. And what is specific about our functions is they tell you what resources are required to execute them. So whether you need a GPS sensor for it or a certain other sensor, or you need some data. So if the data are in the key value store, we can give the key. We know we need this information, right? And we can take this into account in scheduling these functions. So basically, this will be all decided here. There is a resource manager which is responsible to manage these resources and the battery here. Then you have the invocation, which is basically the function to execute. It's the events, copies of the events that came in that carry the data, right? You have the specification of the resources that are needed, and you have also a deadline for it. And so the deadline is obviously also important when you take decisions when and where to run something, right? And then the dispatcher is only responsible to forward it to the local accelerator, to the thread pool that is running on your standard processors. You can forward it to the edge and to the cloud, no? Good, so that is basically implemented by a student, and we are continuing this since maybe a year or so. What we currently have is an automatic deep sleep, for example. No one has this. So you have light sleep in these machines where actually the memories are kept, and that is easy to do. Going for a deep sleep is difficult because you lose the information in memories. So you have to manage this correctly, and we can do that. So the system analyzes which triggers are there and decides how much time is there to sleep, how much time it needs to wake up, and then takes decision to go for sleep or not. So we have function offloading to the edge, at least a prototype. We have a coffee machine, you know that. And we take, we take the images of the display to understand what coffee was taken. And so we are able to either do the inferencing on the board or to offload it transparently to an edge system, which would then run a neural network-based inferencing scheme there, right? So it's not a general implementation, but the concepts are there, and that has to be extended for the more general case. We are in the process to develop, and we have a prototype, which does automatic duty cycle management. So in that, you actually wake up your sensor periodically to do the measurements. So you can imagine that you have, let's say, a min frequency, max frequency to do that. You have a battery, you have energy harvesting. So you actually want to influence this frequency to make sure that your system survives at least 14 days. We take the prediction of the sun irradiation or so. So the sunshine, the watts per square meter. We predict for the two weeks what happens. And then we decide how to set actually this periodicity to actually achieve that we have at the end of the 2 weeks, whatever happens is predicted for the sunshine, we still have battery. And that is running while I'm here, and I brought this diagram so you see we can harvest some energy and are above zero at the moment. We do shift tracing. That is interesting for the performance analysis guys here. And there is hardware for that. Who spoke about hardware? That we don't have hardware? We do. So these processors actually have special tracing hardware, onboard memory, and you read it through the JTAG interface, so you don't influence the execution on the cores, but you just have a hardware bypass. So we use this, and we use the protobuf binary trace format. I really hate this JSON-based trace stuff. Yeah, you waste so much space for that. And so you can look at internals of the CIF execution. You can see the queues for the events and all that stuff. And you see the invocations, and they are blocked until all the events arrived, and then actually they start executing here. So we can do this. You can look at the resources, and these things are today for free. Yeah? You use Grafana, and a student can do that in a week to put up these diagrams. Good. The use case is senior home care. Obviously motivated by the statistics, right? You see, in Germany, these are the number of seniors that need care, which are at home, and these are the ones that are in a nursing house. And you see that the number explodes, right, for those that actually need help in daily life in Germany, right? And what you get is today to monitor these guys is really very, very low stuff. I mean, you have these sensors where you can signal that you have a problem. You have these baby phones. That is basically the level currently we can support this. And I know my father was in Krefeld, right? We were in Munich, so you want to know more. What's going on? Is there any dangerous situation, or is he doing well? Yeah, and so you want to understand the habits of the person, and when the habit changed, you have a problem, right? And so that is what we are going to do. We use this infrastructure to actually learn the behavior and detect anomalies automatically. We are not concerned about money. So looking at these numbers, these are the numbers in Germany for a place in a nursing home that you have to pay. In addition, yeah, the price is higher. So about over 2,000 euros. And you can go for a private nurse, which is also 2,000 euros, more or less, if you get a Polish person, for example. Yeah. And so people, if we can enable them to stay at home for half a year more, they save so much money that they can pay easily for a fanless edge system or whatever, right? So that is basically, I think there is business behind that you can do. And we currently run a lab course to develop this. We basically have the following. So we have our IoT platform, which acts as a data storage. So basically these sensors report to that. Then we have a digital twin, which learns these habits. So basically you apply modeling there, and you can do anomaly detection, right? And with the anomaly detection, you can inform what we call a senior monitor. That would actually then decide whether it needs more information or inform the caretaker about something and so on. As an example, we have an intelligent bottle, right? So a very important problem is that the water intake of seniors is good. So we basically equip the bottle with weight measurement, and wherever you put it, when you put it down, we measure how much water is still in there. So we can learn automatically what the water intake is. So to actually do experiments, we implement a virtual apartment. So you define scenarios and you can do time warping. So you can actually run a whole month in an hour or so, right? And you can see how the system behaves. All that uses the FaaS, which is on the edge cluster that we provide to the students. And in principle, it could overflow to the cloud, but we don't use that at the moment. So we will see on Friday what they achieved, so how far they get with it. But I think it's on a good way to become a basis for evaluation what we are going to do in the Serverless IoT Framework. Right, so that's all I have. So you see, I'm sort of going back to the roots that motivated me to go to computer science, right? And performance measurement, and so all these things will be there as well. Yeah. Any?
I have a question.
Yeah.
So how do you get now data for this use case? How do you get data?
Well, so at the moment, these are sort of artificial data, right? We create we define a certain scenario, and we have some statistical changes there, right? Right. So obviously, the next step would be to deploy something somewhere with real seniors. That is not easy. We try to get into contact with these agencies that do the caretaking and so on, and also to learn a bit more about what seniors would accept or not accept, right? And so I'm very convinced we should not do anything that requires them to do something for us, right? So we have to do it in a way that they are not really necessary to interact with a technical system or so. Yeah, I think that will not work at the end.
But still, it's personal data. This is
Right.
super critical, right?
Yes. So therefore, we decided not to go for elderly homes. Too many rules, too many regulations. Okay. So we go for the private sector. Yeah, you have to sign. You want this, huh? And we want to do it like a privacy shell-based thing, right? So the first step would be you just have a local edge system. It's not connected to the internet at all. It's only learning, right? And the caretaker can come once a week or see whether something changed or so, no? So, and then you can use only peer sensors, no cameras or so, yeah? So you have to offer a certain set that someone is willing to accept, right? And while you get older and you need more help, you are definitely willing to accept also that, for example, your son is able to switch on a camera if something happens to actually see whether there is really a dangerous situation or not, right? So that is basically how we want to take this into account, yeah.
And what data do you really collect? Like you have a camera, you have a heartbeat?
Currently, we have a heartbeat monitor. We have this bottle. We have a camera. We train it with images of persons that fall, right? So there are such data sets. So, and then you can detect, dangerous situation that someone fall and cannot stand up again. We have obviously temperature sensors. So we have one group that is excited to detect a fire in the kitchen. Yeah, and I think that's currently what we have. But an important area is also medication. So there are like painkillers. How much painkillers do you give? And it's a big problem. The doctor comes, after 2 weeks and asks the person what happened. And you know, so they don't record what they did and so on. So you could actually maybe help also in such decisions. So that is, I think we can do much more than is actually done with the help of this technology, right? So we try to do something in that direction.
Yeah, I have two questions. So the first one is technical.
Yeah.
Is the how computationally demanding is this application? Actually, do you really need to care about performance? And the second question is, this seems to be something that you could commercialize at some
Yes.
point. Do you have plans for that?
So to the first question, I think we are a bit lucky here. So you don't have hard real-time requirements. We don't want to process 30 frames per second and do object detection and so on. So that enables us to do things on the small device, yeah, and might be slow, but might take too much energy. So maybe the edge is also important in that respect, right? We also have some work on neural network splitting and early exits. So you can run a neural network on the small device. And if you have a high probability for a certain situation, you don't even have to go through the entire neural network for that, right? So we are exploring this as well to reduce the requirements, right? So I think it's not that demanding, but if you want to do modeling, for example, yeah, you collect data over months and so on, and you have to do modeling to detect the normal behavior and anomalies. That is quite a bit demanding, right? And so if you have on the edge a cluster for FaaS, you can easily scale. You sell just 2 of these machines to the guy and, okay, so with commercialization, I fully agree. I think there is huge potential for commercialization here. And, but as you know, yeah, so you need to find someone who wants to do it. We are in contact with companies, but they are all focusing on nursing homes. So this sector of the private people seems to be not in the focus, right? So I think it could be done. Maybe someone of the students or so wants to try, right? So we actually make sure that all the software we develop is under the MIT license and can be used in any way afterwards. So they have to sign it if they go to our lab that they agree.
One more question. So to me, so for such cases, for such scenarios, I think there are 2 cases important. One is the person experiences an emergency but is still be able to speak.
Okay.
So then that person can simply make a call and explain the situation.
Mm-hmm.
And the other situation is the person is no longer able to speak. For example, the person falls down the stairs and is unconscious in such a situation. So the question is, would it be enough maybe just to detect cases where the person is no longer able to speak? And if those cases are rare, you wouldn't need to really fully understand that situation. You could simply send someone to check.
So I think the applicability of this goes much beyond just detecting such an emergency situation. Yeah. And the second point is speaking is for seniors. It's an interesting problem. Yeah. So my father had this. Yeah. I notify someone, and you have a speaker somewhere in your apartment which is connected to the normal phone line, and he was not hearing well. Right. Yeah, all these troubles are there, and I think it would be much better if we could detect there is a situation and you can inform someone. Yeah, so it would be interesting to use federated learning, for example, to train this speech detection networks or so, specifically for the senior, right? So that would, yeah, you could actually combine information that you get from all the apartments, but you have to specialize it for the person because the pronunciation and so also gets a bit difficult at the later on. So that is something we discussed already, that you could do this, and then you have this even the training has to run on the edge. Then you don't want to give the private data to the cloud, yeah, but you want to profit from learning from a wider group of people. No? So a lot of opportunities are there, and I think it could really change life for all these people. And in Germany, that will be an exponentially growing group of people, right? Okay, so let's stop. Yeah.
Some 20 years ago, I supervised also a PhD thesis with a topic on a smart carpet that was produced by Vorwerk and Continuum. And they had something like, I checked it here, 20 sensors per square meter. But it seems that they discontinued that because there are no recent links on that. But they just wanted to use it for the same, or in addition for these.
Absolutely, a great idea. So I went to a TUM. What is this? Where they train teachers, right? And they actually have a digital lab, and they have a kitchen there, and the whole kitchen has a floor which is sensitive. What you say? Yeah. So that is nice, but I fear that this goes beyond what a senior would do to his apartment. Yeah, establish such a floor everywhere. So I think we can do quite good with cameras, for example, to detect. Yeah, but I mean, there are so many things, and lots of sensors could be used there, and new ideas for sensors. So I'm quite optimistic that I have interesting years in the coming years. You want to say so?
Yeah, I have one question regarding, because you put up the problem of energy awareness on the edge and the IoT.
Yeah.
And the first problem is IoT devices, as far as I know, they're not standardized. So whatever you put there, monitoring feature, software you can put there, it's under control of proprietary platforms. So it's a bit hard. So I wonder, because you want to put containers there, function as a service there, how do you deal with the problem that there's a jungle of weird hardware?
We develop our own hardware.
Yeah. That's the first point. The other point is, I don't know how your platform is if it's implemented with Java, running a JVM even on some edge devices could mean you can't run a use case anymore because there's no more memory available.
Okay.
If you put some of the software even on IoT devices, or your key value storage, I mean, you put so much software there, the use case will not fit.
So the approach we currently have is you deploy the function to the different layers, and you have a normal C implementation of the function on your monitor, on the sensor, right? On the edge, it's packaged into a container and can be run on the FaaS. Yeah? But it would be very interesting, and he's the expert for that, to use WASM, for example, for that. Yeah, so you get the isolation, but a very low overhead for that, right? So we want to explore this as well. That could be a way out of that problem. Yeah.
Well, there's some discussion. Some people move from Java to Go in order to deal with that thing because it's really tricky.
Our edge devices were Raspberry Pis and these little devices, and I talked to someone in Intel and he said, oh no, forget this, you need the real computers there, right? And therefore we went for the fanless things there, but you have like a gigabyte of disk, and you have some gigabytes of memory, you have a processor there, so it's a substantial machine. Yeah, and at the moment that is not limiting what we can do with our platform here, but hopefully it will be limited so that we can actually also investigate scaling out, right? So, but we have to stop really. Yeah, it would be a pleasure to discuss a bit about that, during the rest of the time here, but I have to hand over to Mohak, and this will definitely also be interesting to you. Okay, thank you.